When you're doing the analysis of a graph and looking at everything an accurate graph will entail, the first thing you should note is this is a polynomial. Its lead term is x cubed. So we should expect that the left end is going down and the right end is going up. That should not be anything new. But what the methods we have learned in chapter 4 so far is going to allow us to do is to allow us to make these graphs as accurate as we've ever made them before. So the first thing we want to do is we want to start with our first derivative test to find our intervals of increasing and decreasing and local mins and maxes. That's what that's going to tell us. So if we do the first derivative, we get 3x squared minus 12. Now, if we set that equal to 0, it's only going to have critical points based upon the fact that the first derivative equals 0, and the first derivative equals 0 at plus or minus 2. Now, when you inflict the square root, please make sure that you're including the plus and the minus. If we make a plus and minus chart for the first derivative, you can, since I didn't actually factor it, which I could have, I am just going to think about, I'm going to plug into the entire thing. Okay. So let's do test values of -3, 0, and 3. If we plug in -3, we get 3 times 9, which is 27 minus 12, which is a positive. If we plug in 0, we get 0 minus 12, which is a negative. If we plug in 3, we get 27 minus 12, which is a positive. So before you go further, let's write down what that means. So it means that it is increasing from -infinity up to -2, and then again from 2 to infinity. That is these portions here. Now, increasing, decreasing, and concavity do not use brackets because those switchover points are not included. So just get in the habit of using parentheses for those. And then our function is decreasing between -2 and +2. Now, we should also label, if we know anything about the points at -2 and +2. At -2, we're going up and then down. So when x equals -2, that is a local maximum. At +2, we are going down and then back up. So at +2, we have a local minimum. So our first derivative test is done. We know that the points -2 and +2 are really important. Okay. So now let's go and do the second derivative. So if we go back to our first derivative and we look at the, taking the derivative one more time, we get 6x. Again, polynomials work for everything, so we don't have to look for undefined values, but we do have to look where does 6x equal 0, that's at 0. So the only point that might be a point of inflection is at 0. Now remember, a point of inflection is where the curvature of the graph changes, where the concavity changes. So a cup that is down and a cup that is up have met. So that might happen at 0, it might not, but how do we do it? Well, we do the same thing we did before. We do a plus or minus chart. So let's plug in -1 and +1 into our second derivative. For our second derivative, if we plug in -1, we get -6, so that's a negative. If we plug in +1, we get +6. So 0 is a point of inflection. A point of inflection is where the concavity changes at a particular point. So that has to be a point in the domain, or it's just, yeah, okay. Now we have to list the intervals of concavity. So it is concave up from 0 to infinity. That's where the second derivative is positive. It's concave down from negative infinity to 0. So the points that we should be very, very concerned with when graphing a polynomial are the local mins and maxes, the points of inflection. Now, it is not a bad idea to plug in some other points, but let's put in what we know first, and then we'll see where that leads us. How about if that's a positive? Okay, so now we are plugging in points to the original to see where the heights are on the original. If you plug in -2, you get -8 plus 24 plus 2, which is 18. If we plug in +2, we get -2. And if we plug in 0, we get 2. Now, it is a polynomial, so there's lots of things that we know. But, but let's just put in what we know so far. Excuse me. Okay, so I'm going to count my y's by 2's. My x's I'll just count by 1's. Okay. So at -2, we are at 18. Now remember, that is a local max. At +2, we are at -2. That is a local min. At 0, we are at 2. That is a change in concavity. Now, let's put the pieces together. Now, if x cubed minus 12x plus 2 was a quadratic, I would definitely find the zeros. You know, where is it going to hit the x-axis to be a little more accurate? So this isn't going to be super accurate, but let's, because we have -2 plugged in, I'm going to plug in -3 just so we get a sense of where it's going down, okay? If I plug in -3, I get -27 plus 36 plus 2, I get 11. So it hasn't come down a whole lot yet, but so at -3, 2, 4, 6, 8, 10, I'm right here, okay? So what do we know is happening? Well, it is concave up, concave down until it hits there. So the curvature has to be a cup that is upside down. We are increasing to this point, then we are decreasing, okay? So do you see how my concavity is like an upside down parabola? My cup is down. At 2, my cup, or I'm sorry, at the point 0.02, my cup has to flip up. So, and I have a local minimum at the point we see there at 2. So it has to be an upside down cup for the remainder of the graph. So what I want to see on your graphs is I need to see those important points. If you can plug in more points, plug in more points. The more accurate you are, the better. But your curvature should match. Your increasing, decreasing, your local mins and maxes should all kind of flow together, okay? Now we're going to do one more together that's a little more difficult, and then the rest are on you. Okay, so let's look at our second one here. We're going to do x times the square root of 6 minus x. Now, knowing that it's a square root function, it's very important that you recognize where the domain is. Like, where does this graph live? A polynomial lives everywhere. We saw that first one. It exists. It's wonderful and great. This one doesn't. But if we remember what we learned, hopefully in pre-calc, 6 minus x is greater than or equal to 0 is the domain of a square root function. Just where is the inside stuff greater than or equal to 0? That's where it's going to live, because that will put positives in there. If you solve that, you get negative x is greater than or equal to negative 6. X is greater than or equal to 6. So I know this graph lives, I'm sorry, it would flip my symbol. I divided by a negative, flip the symbol. So my graph lives everything that's less than or equal to 6. So keep that in mind, that the graph is to the left of 6 and then stops, bam, stops at 6. Okay. So let's think about when we learned derivatives. When we first learned derivatives, I would tell you to rewrite that to a 1/2 power. Now, if there was a way to avoid the product rule, I would avoid it. There is no way to avoid the product rule. So that's how you have to do the derivative. So our first derivative is first times the derivative of the second. Now the second is a chain rule. So you have to drop the power down in front. Stuff stays there, power goes down by 1, but don't forget to multiply by the derivative of the inside. Okay, so I did the first. This is the derivative of my square root, plus the second, just your square root part, times the derivative of the first. Now, at this point, I know some of you struggled last week of how to handle that. How do you get it so that you can factor it and find those critical points and stuff? Here's the key to these. You always want to look at the lowest power on your 6 minus x. So there will be a lowest power, and that is what you want to pull out. And you want to factor that lowest power out. You always want to factor out the lowest power of that thing. Now, if they all had an x in it, like this plain old x, we could factor out an x. If they had any numerical components, but there isn't, okay? Now, if I take this out of here, I am left with an x, a 1/2, and a -1. So a -1/2 x. So make that nicer. When you divide out something, you subtract the power that's there. So if I subtract a -1/2, what do I get from this power? If I subtract a -1/2 from 1/2, you get 1. And that's why you do that. It should always work out that way, that you should get a whole thing when you're done, okay? So that's just one of those. And then the one there didn't affect it. If the one there was a number, like if that was a 2 or 7 or whatever, put that in parentheses and put that there. But since it's a 1, we don't really have to. Now let's make that bracket thing a little nicer. A -1/2 x minus x is -3/2 x plus 6. It's in factored form now. If there's any other way you could factor it, you're welcome to do that. Now, we are looking at where that thing equals 0. So we're looking where that thing is equal to 0. This part here is really 1 over the square root of 6 minus x. And that is not going to ever equal 0. But it is undefined at 6, right? Because if we thought about, we can't have a 0 denominator. It is undefined when 6x equals 0 or at 6. Great, okay? So that is a critical point. So fractional exponents have critical points usually where their denominator equals 0. So that is a critical point you don't want to forget. Now this critical point is a little nicer. You know, that's just solve. So subtract 6 from both sides. Multiply each side by negative 2/3. So that would be 4. Okay, so we have 2 critical points. We have 6 and 4. Now 6 is on the border of our thing here, so but we had to plug in 6 anyway. 4 is not in our border, so 4 is going to be something nice. So let's go ahead. We don't need to plug in something over here. Our function does not exist over there. So don't waste your time. Okay, our function, you would get an undefined, you know, like a negative under your radical or something stupid. So, okay, but we don't need it. If we plug in 4 to our first derivative, so I am thinking of plugging it in here, okay? And I'm plugging it or here, however you want to do it. Okay, so if I plug in 4, that's a positive, right? 6 minus 4 is a positive. If I plug 4 in here, what is that? That's going to be negative 6 plus 6. Is that 0? Oh, I don't want to plug in 4. I'm sorry. How about if I plug in something between them? Let's do 5 and 0. That's why we got 0. I've lost my mind. Okay. Anyway, let's plug in 5. 6 minus 5 is 1. That's a positive. Negative 3/2 or negative 1.5 times 5 plus 6 is a negative. So positive times a negative, that's a negative. Now I'm going to plug in 0. I'm going to get a positive, and a positive, that's a positive. So it's going to be increasing and decreasing, and then it stops at 6. So we'll include 6 when we plug in some points, but we don't call it anything more than it's the end of the graph, okay? So we know that x equals 4 is a local max. And it is increasing from negative infinity to 4. It is decreasing. You only have to include from 4 to 6. There's nothing after 6. This graph stops at 6. We are definitely going to have to plug in 4 and 6 into our original function to see where those 2 points fall, because those 2 points are going to be really important to us. Okay, now unfortunately we got to do the second derivative. Oh goodness. So I'm going to be looking at this, and I am going to have to do, unfortunately, the product rule again. It's a gross product rule, but we're going to do what we can do, okay? So it is going to be the first times the derivative of the second. It's just a negative 3/2 x, so it's negative 3/2, plus the second times the derivative of the first. Now what do? We drop that power down in front, leave the junk, power goes down by 1, derivative of the inside. Okay, you always can remove the lowest power. What's lower, negative 1/2 or negative 3/2? Negative 3/2. So we're going to take out a negative 3/2. Also, I notice that these are both halves. These are both negatives. Let's take a negative 1/2 and just kind of throw it right there. Okay, so what are we left with? We're left with a 3. Now, remember, that was the lowest, so we took that one out. But what is negative 1/2 plus 3/2? Negative 1/2 plus 3/2. positive 2 halves or positive 1. So that should always happen if you did it right. Now, I'm not going to write the first, but that's the first power. So we're left with a 3 and a 6 minus x. Okay. So we took this one out. That's gone. I took out a negative 1 half. That's gone. So I am left with a negative 1 and that. So I'm just going to put a negative in front of that. Okay, we're getting there. We're getting there. See why I did this one with you? Okay. Because it's disgusting. I'll probably give you one more like this. So let's distribute that negative. If we distribute that negative, then we can combine like terms. Oh, yeah. Okay, so 18 minus 6 is 12. Negative 3 plus 3 halves is negative 3 halves. And our second derivative is undefined, still at 6. So 6 messes it up. And then 12 minus 3 halves x equals 0. When 12 equals 3 halves x, so x equals 8. Please check my math that I'm right. That's 24 divided by 3. Yeah, 8. Okay. So now we're going to make a second derivative chart. Actually, last I checked, 8 comes after 6. Oh, is 8 in our domain? No. So that cannot be a point of inflection. It doesn't. There's nothing over there. 6 is an undefined point. Points of inflections are points on the graph. That is not something we have to concern ourselves. But we just have to check, is it concave up or concave down? So it's looking as if this whole piece is either like a hook like that or the opposite, like a hook like that. I don't know. Okay, so I'm going to plug in 0 again. And unfortunately, I got to plug it in here. Okay. If I plug in 0, I get negative 1 half times a positive thing, don't care what that thing is, times another positive thing, don't really care what that thing is, and it's a negative. So it's concave down from negative infinity to 6. There are no points of inflections or inflection points. So really, the only point we found initially where we had that local max was at 4. So we're just going to have to plug in 4 and 6 and maybe a few other low points. Okay. Let's plug in 0, 4, and 6. Just I know. Okay, so let me write down the original function. So our function, what was it? X square root of 6 minus x. Okay, so if we plug in 0, we get 0. If we plug in 4, we get 4 times the square root of 2, which is about 5.7. And if we plug in 6, we are back at 0 again. Now, it's increasing till 4, then decreasing till 6. The concavity is concave down, so our cup is upside down. So let's draw this. At 0, we're at 0. I make this really good straight lines. At 4, we are at 5.7. At 6, we're at 0. And so our graph Looks something like that. The more points you plug in, the more accurate you're going to be. And then you can check in Desmos that what your graph is doing what you think it's doing. You can see we have a point at 60. We have a maximum at 5.7. We go through 0, 0. It has a concavity. We can see it is concave down for the entire length of the graph. We can see that it increases till here and then decreases. So all the things that your first or second derivative tell us should show up in the graph, or either your math is wrong algebraically or your graph is wrong. Okay, so that is that. Okay, so here is your job to continue this and bring this back to me tomorrow. You're gonna have 2 problems. Number 3.
3 is gonna be like 1, and then 2 or 4 is gonna be like 2.
You're so smart.
How many? Wait, you said what?
2. There's only 2 more problems.
Oh, I think, well,
Only.
just leave the square roots out, please.
She's not
gonna.
Or not, the
Square roots are
And the product rule. You could have just not made it a product rule.
You could have, but like, did you?
Could have just been the one function rule. No.
We're getting to those.
Let's not.
Yeah.
Actually, let's skip that section.
So you need these done when you